My screen visible, right? Oh, no, no, no. Why I am going for this? No, I have to go for this, right? CRE2. Yeah. So, shall we start, ma? Think, so, let us start from where we left. What is the last period for you today? Yamini?
Professional electives, sir.
Professional elective. It is going to happen. Class is there. Professional elective. What is
Yes,
it?
sir.
Okay. What I thought of taking 2 hours so that I can have. Yesterday I lost one period. Nah, I can get back. I thought. Okay. So you don't want to give extra period to me. Okay. Okay. We'll try to complete as soon as possible. So in the first unit, we are discussing about the batch reactor, and the second unit is the continuous reactors. Some of you can mute. I'm getting some disturbance. Yeah, okay, thank you. So, in continuous reactor, there are two ideal reactors. Ideal in the sense it is ideal, right? So, whatever the reactors, what you are seeing in companies, all that, it's not an ideal. There will be some non-idealities. You are expecting you will expect a conversion of around 90% in some reactor, but that 90% you may not get because of the non-idealities. What are the non-idealities? All that we'll study in the fifth unit, not now, right? Let us not waste the time. Why where there will be non-idealities, all that. But what we are studying now is the real reactor. That is ideal reactor, where you are assuming something and telling that if you assume this, your reactor becomes an ideal where whatever conversion you are expecting, you are going to get it. But in reality, it won't come. Just like ideal case in the sense all should get S grade or O grade. But there will be distribution, right? So all people may not get S grade or O grade or whatever grade you maximum grade. Because of some non-idealities, some students may not study, some students may not submit the assignment, some students just like that, right? So even in the reactors also, there will be non-idealities. So what are the non-idealities? All that we'll study in fifth unit. There are two types of reactors, continuous reactors, mixed and plug flow. Mixed reactor is nothing but a batch reactor where there will be continuous input and continuous output. The contents inside it will be stirred so that you get a uniform concentration. Here one important assumption is with whatever concentration the product is leaving, that concentration will be equal to the concentration which is inside the reactor at that particular time. With the time it going to change, but at a particular time, whatever concentration here inside with the same concentration uh, with the same concentration that product is coming out. Whereas in plug flow reactor, this is not like a tank reactor. It is like a tube reactor where the contents are entering into a tube and exiting from a tube, and the reaction is happening inside the tube along the length of the tube. The tube can be curved like this, or tube can be just straight pipe or whatever it is, right? So just to show you that pipe can be anything, he showed you like this, S shape or something like that. So if you look in the real things, it may not be curved. It can be a straight pipe also, right? So don't think that plug flow reactor always it will have this kind of curvy design or something like that. Plug flow in the sense it is going to a tube. So along the length of the tube, the reactants are reacting to give you the product. Here one important thing is the concentration. Here there will be one concentration, here there will be one concentration, here there will be one concentration, here there will be one concentration. That is, the concentration changes with the length of the reactor. Whereas here the concentration at any point in the reactor is uniform at a particular time. At a particular time here, the concentration will change along with the length of the reactor. So now you know here the concentration is changing only with respect to the time. So you get a differential equation here, correct? Because dou Ca by dou T or dCa by dt. Here what is happening? The concentration will change not only with the time, even with the length, position. So you get a partial derivative. So you should know what is the, there are three derivatives. One is derivative, partial derivative. The third one is total derivative or called as substantial derivative. So if you will look at that particular thing like this, you write. So one second, let me write here so that. Wait, what happened? No thing is. One second. Hey, I'm unable to write. What is happening? Ah. Yeah, here I am writing. One is dt, let it be dCa by dt. That is nothing but the change of concentration with respect to the time. dt is the time. The other one is dou Ca by dou T. And the other one which we won't use here, but in 7th semester you will be using in transport phenomena is dCa divided by dt. There is difference between this d, capital D and dou. So you should clearly understand what is the relationship between these three. All the three is derivatives. This is called as ODE. This is called as ordinary differential equation. So your change is only in the one direction. The only direction is the time or x, whatever it is, right? That we call as the ordinary differential equation. You get partial derivative dou Ca by dou T. This is called as PDE, partial derivative equation, when the change of concentration with respect to time and x. X is nothing but the length of the reactor, any particular length. So the concentration is changing not only with respect to the length, even with respect to the time. Then you get partial derivative. The other one is capital dCa by dt. This we call as substantive derivative. Substantive derivative. I don't know whether you got this derivative or not. This is one derivative. One more important thing we'll get it here, right? So right now we'll be discussing only about these two. In 7th semester transport phenomena, there is one subject called transport phenomena, TP. In that you will be studying more about this substantive derivative. So as long as your derivative is this fellow, ordinary differential equation, your life becomes very simple. Because any simple Euler method or Runge-Kutta method or Runge-Kutta RK method, any method is there to solve this differential equations. But if there is a partial differential equation, this partial differential equation again should be converted to ordinary differential equation by using some similarity variables. By using some similarity variable methods, some variables you have to add so that the two derivative is shifted to one derivative. Then it comes to ODE. Then ODE you can solve by this, like this method. Understand? So this you get ODE, but this we get PDE. The differential equation, if you solve the material balance, you get PDE here, you get ODE here, right? So, but in this, we'll make this PDE as ODE and then solve, right? We'll see how to do that, right? Again, I'm telling you, a lot of mathematics will be coming here because chemical engineering, without mathematics, there is no chemical engineering. Because chemical engineering, too much of emphasis on mathematics, especially differential equation solving. We get too many. That is why we are having one separate subject called as applied mathematics in chemical engineering, right? So you have to be a bit strong with the mathematics, whatever you studied earlier, especially second semester differential equation solving. Right? Yeah, we'll see now. We discussed in the earlier class what is space time and space velocity. These are two important 2 marks question. The space time is the time required or the time necessary to process one reactor volume of the feed. Now, if this is a reactor inside, if this is a plug flow reactor and this is a plug flow reactor, this is the inlet and this is the outlet. So this let some volume, this volume of the reactor is V divided by the flow rate is V naught. That V naught is the flow rate through which volumetric flow rate through which the raw material is going. So the same volumetric flow rate, the volume fluid will come out. Therefore, the entire volume divided by the volumetric flow rate will give you the space-time tau. The volume is having a unit of meter cube or liters, whatever you want to put. And volumetric flow rate will have a unit of meter cube per second. Therefore, this gets cancelled. Tau will have a unit of second or minute or hours. So very important, space-time is the time necessary to process one reactor volume of the fluid. This entire volume of the fluid, this particular molecule is coming here. This particular thing is going to be the last. So this entire stretch, this particular thing going out, how much time is going to require? That is what we call it as the space-time. The other one is space velocity. It is a number of reactor volumes of feed fed at a specified conditions which can be treated in a unit time. So here you are calculating how much time is required. Here you will see how many reactor volumes of feed. That is nothing but per second how much reactors volume of the feed is being processed. So it is nothing but 1 by inverse of this. That is what you do. Tau is nothing but V naught by V. V naught you can write as Fa naught C by Ca naught, that we will see now. Fa naught is the molar flow rate and Fa naught is the Ca naught is the concentration. So if you do that, you get V naught. So Fa naught C naught by V naught V will give you S. That is nothing but the space velocity. Here one more important thing is there. This space time, you get one more T bar, that is nothing but a mean residence time or called as holding time. So you have to differentiate what is this tau and T bar, that is the mean residence time or holding time. So mean residence time, what do you call? Mean residence time is nothing but how much time is how much time the molecule is spending inside the reactor, right? So you have to give clear definition for this. If your what do you call? If A is giving you R, and if there is a number of moles same, that is inlet and outlet, and there is no expansion factor, then what will happen? All the times will be same. But A is giving you 4R, like gas phase reactions, or 2A is giving you some R, where there is increase in the number of mole or decrease in the number of mole, especially for a gas phase reactions, then these times will differ. Because there is expansion, just like I told you, one example, popcorn. Popcorn, initially it is a seed this much, but the moment it comes here, it gets popped. It is occupying more volume. Therefore, the time of this molecule, if it is not popped up, it stays a bit more time. And if it, since it is popped up, it moves much for what do you call less time. So expansion factor will make this times different, right? So yeah, that you have to be very clear. What is when this times will change. So let us do the performance equation for this reactor, that is mixed flow reactor. MFR is called as a mixed flow reactor, or CSTR, continuous stir tank reactor, right? So this is called as a performance equation. Performance equation, right? Performance equation. So we need to do a material balance. Again, we know that how much is inlet is equal to how much is outlet, how much is reacted, and how much is accumulated. So four things, that is what: input, output, disappearance, and accumulation. Now this is a flow reactor. During the flow reactor, how much is going in, that much is coming out. That is, the flow rate is same. Therefore, accumulation will be 0. Yeah, you see the material balance of A over a reactor is input minus input is equal to output plus disappearance by reaction plus accumulation. Since it is a steady state process, we are doing a steady state material balance. If you want, you make a note of here steady state. Yes. Steady state material balance. That means when you call steady state, when the flow rate is not going to change with respect to the time. How much is going in, that much is going out. There is no accumulation at all. Just like you are filling a bucket. Once the water reaches the bucket, top of the bucket, then how much water is coming in, that much water will be spilling out. That is what is the steady state. At that process, the rate of accumulation is 0. Here, everything is rate. I didn't write it, but generally we won't write, because material balance you will put for a time, per unit time. So this is the rate. So the rate of input is the rate of output plus the rate of disappearance plus rate of accumulation. The rate of accumulation is 0, but accumulated will be there. The rate, the change of the accumulation. Rate in the sense it is change. The change in the accumulation is 0. That does not mean that accumulation is not there. You understood the difference between the rate of accumulation and accumulation. Now I'll give you one example so that you will understand much better. Yeah, 1 second. Now you see 8 minus 5 is 3. Even 6 minus 3 is also 3. Yet the accumulation, rate of accumulation is 0. That does not mean that there is no accumulation. There is accumulation, but the rate at which the accumulation is there, that is the change. The change in the accumulation is 0, right? This is 0. So you have to write these 3 terms: input, output, disappearance. Now can we write the input? Now let us get this terms into picture now. This is the tank. This is the stirrer, which is moving in one direction. Let us, this is the input and this is the output. Input, initially the concentration is Ca naught. Initial conversion is Xa naught, which is 0 because there is no conversion. I am just writing this reaction for this. This thing for A gives R. So this is some K. I am writing the disappearance of A, right? So that is why everything is A, right? Ca naught is some value, Xa naught initially, there is no conversion. The full Xa is there, therefore initial conversion is 0. V naught is nothing but the flow rate. Fa naught is nothing but the molar flow rate. V naught is nothing but the volumetric flow rate. So at final, we'll let us put CAF is Ca, that is concentration of A at the final. Let it be, some books they will write CAF. Generally they write Ca. XAF is XA because there is a conversion. XA is converted to R. That is why we are not putting 0. Initially there is no conversion. Only A is present. VF is nothing but V naught or the molar flow rate, that is volumetric flow rate. There is no change in the volumetric flow rate. That is what you are putting here. RAF is nothing but the rate, final rate is nothing but a rate minus RA because you are assuming there is uniform concentration here. Therefore, final rate will be equal to normal rate. Then FA is nothing but the molar flow rate outside. FA naught is the molar flow rate inside. Outlet molar flow rate is this. The concentration is uniform inside the reactor. The volume of the reactor is V. The conversion is XA. That is the same XA you are putting here. Because if conversion is XA here, here also it will be XA because that is what you will assume in CSTR, that how much is the conversion inside, that much is the conversion outside. Ca is nothing but the conversion, concentration. That is the same concentration you are putting. The minus RA is the rate of for that particular concentration. The same is at the outlet, right? Now we will write the mole balance. So input of A, that is what here you have to write. We are writing in terms of moles per time. That is nothing but what do you call mass balance. Mass balance always will be in terms of moles per time or kgs per second or something like that. Whereas energy balance will have kilojoules or joules per second. Since it is rate per time, you have to put here rate you can write add. I think I missed that rate. In no books they'll give like that. But when you are writing the rate, input is nothing but the rate. Here also rate. Here also rate. But no book will write because anyhow, because mass balance, this is a steady state mass balance or transient mass balance we call, because then you are writing rate per unit time. So input is nothing but Fa naught. That is what is here. Fa naught is Fa naught into 1 minus Xa because the conversion. Xa naught is 0. Initially there is no Xa. There is no conversion. Therefore, input molar flow rate is Fa naught. That is what you are putting here. What is the rate of the output? Again, moles per time. When you are writing in this equation, this is the mass balance. Each and every term should have the same unit. If you are writing an energy balance, it should be kilojoule per second for everything or joule per second. If you are writing a mass balance, then it should be kgs per second or moles per second if you are writing a molar balance. 1 second, let me drink water. Yeah, rate of output again moles per second is Fa. That is what we are putting. Fa, you already know that Fa is Fa naught into 1 minus Xa. Right? So disappearance, what is the disappearance term? Disappearance is nothing but minus RA into V. How you are getting this minus RA into V? Can anyone tell how you are getting this minus RA into V? We know that minus RA is 1 by V into dCA by dt, correct? So this is minus will come, right? Minus RA. So minus dCA by dt is nothing but the disappearance. That is what is this. Disappearance, the rate of disappearance is nothing but minus RA into V. That is what here. Okay. You know this, right? We studied in the first unit. Based on this only we got all the things, right? The rate of A is disappearing or the rate is minus 1 by V. V is the volume of the reactor. dCA by dt, the change in the number of moles per unit time. Minus dCA by dt is nothing but the disappearance, the rate of the disappearance. Minus tells you disappearance. That is nothing but minus RA into V. That is what. Now you substitute entire thing here. Input is FA0, output is FA0 1 minus XA minus RA into V. Yeah, this you split it. FA0 minus FA0 XA minus RA into V. This fellow and this fellow will get cancelled out. So this is a minus. You take outside this. Then FA0 XA is minus RA into V. Correct. So we rearrange something here. We rearrange something here. V by FA0. We can write V by FA0 is XA by minus RA. This is the expression for MFR. This is the expression for MFR or CSTR. V by FA0, that is the volume divided by the molar flow rate, is XA divided by the rate. XA in the sense you can put delta XA because here initially there is no conversion. So XA minus 0 is nothing but XA. That is why in some books they put a delta XA divided by minus RA. What you do, let us write one more way. V by FA0, you multiply by CA0 by CA0 on the both and the bottom and the top. Then what will happen? This V CA0 by FA0. Sorry, we write properly. This particular term. In this, I am just multiplying CA0, CA0 up and down. So V CA0 by FA0 is nothing but tau. That is what we saw here. Tau is nothing but V CA0 by FA0 because 1 by tau is this. Tau is nothing but CA0 V by FA0. That is what we can write. So this if you write as tau, tau by CA0 is XA by minus RA is delta X by minus RA. Right? So we can write the entire equation like this. But we know that tau is V by VA0, V by V0. That is nothing but V by V0. V0 we know already how much it is. So we can rewrite as CA0 XA by minus RA or CA0 minus CA by minus RA because CA0 minus CA is nothing but CA is nothing but CA0 into 1 minus XA. So if you substitute that, you get this particular thing. So final equation, if you write all the three, is V by FA0 is equal to tau by CA0 is equal to XA by minus RA. This is the performance equation for, this is the performance equation for MFR. Very important. Again, I write here, there it is not good. V by FA0 is tau by CA0 is XA by minus RA. These three terms will come. So this is the performance equation. To determine from this equation, we can determine what is the conversion for a reactor. what is the time required for a conversion? If you want 90% conversion, then we can find out how much time it should be reacted. Or if you have some 20 minutes inside the reactor, how much will be the conversion also you can find out by knowing the kinetics of the reaction. If you don't know the kinetics, then what you have to do? You have to find out the kinetics. You have to do some experiment, find out its K and order. K and order is nothing but the kinetics. Then you can substitute in this expression to find out either the conversion or the time required or even the volume required. So how to do that? That is what again we'll draw minus 1 by RA versus XA. So you can see here P by FA naught is nothing but tau by CA naught is nothing but, again I write here minus 1 by RA into XA, correct? I can write this particular thing as like this, right? Now this is Y, you put on the Y axis, this on the X axis, that is what I put, minus 1 by RA versus XA. If I multiply this, Y into X is nothing but the area of a rectangle, am I right? Because to calculate this rate, it becomes very difficult. That is why what people will do is they drew this and then they Y into X into Y is nothing but the area of a rectangle. So whatever conversion you want, if you want some 75% conversion, so you find out the rate curve, then at 75% you draw a line which touch this and then project this on the Y axis. Then the area under the curve, this entire thing will give you V by CA naught, V by FA naught or tau by CA naught. If he is asking you what is the time required, you can calculate from this because you know what is CA naught. Or if he is asking you how much volume of the reactor is required, since you know the molar flow rate, you can calculate the volume. So this is how it will be done using a graph. For using this, they'll give you this data RA versus, that is the rate versus conversion data they will give you. You can do one more way. Instead of XA, you can do this particular thing. XA is nothing but tau is nothing but CA naught minus CA by minus RA. Now you draw this minus 1 by RA versus CA. That is what he is doing here. Minus 1 by RA versus CA. So you know this conversion. This is the initial. You know final. This is the rate curve. So initial and final, this nothing but area of the rectangle again. Wherever final conversion you want, you put a rectangle. Find out the area. Area under the curve will give you this particular thing. This, yeah, tau you will get, or V CA naught by FA naught. If we know CA naught, we know FA naught. Generally, how much initial conversion is there and final what do you call initial molar flow rate, then we can calculate volume of the reactor also. This you are writing with respect to XA. You can do with respect to CA also. Right? Yeah, any doubt, you let me know. Yeah, graphs, we play with graphs especially. Let me I'll delete all this. Now again I will go. Yeah, any doubt here? So the final equation is V by FA naught is tau by CA naught is XA by minus RA. This is the final equation for mixed reactor. If the reactor is mixed, we have to use this equation. V by FA naught is tau by CA naught is XA by minus RA. And I showed you how graphically we can calculate the volume or the tau, the time required for the particular conversion or a particular concentration. Yeah. Shall I go for the next? Now we'll see some examples. Because this conversion, this rate is changing, right? What is rate? Rate is nothing but minus RA. rate RA or minus RA, whatever it is. I have to again pointer options. 10. Now here RA minus RA, I don't know. It's K into CA power N. I need to find out what is the order and what is the rate. Right. So let us assume it is first order. Let us assume it is first order. Then see how this equation is going to change. Right. So let us consider a first order because this is unknown quantity. That is why we are drawing a graph. It's not that easy to get because it changes with the order. So let us assume it is first order minus RA, K into CA. We can write tau as CA naught minus CA by minus RA because we already saw here tau is CA naught minus CA by minus RA. Tau is CA naught by CA minus RA is nothing but K into CA. Now tau K is CA naught minus CA by CA. This is in terms of concentration. We can write in terms of conversion also because tau is conversion is CA naught XA by minus RA. So that is what we get. Tau is CA naught by XA by minus RA. Yeah, how you are getting this? Can anyone tell how you are getting this equation? I don't know whether you are following it or not. I'm just doing V by FA naught is nothing but tau by CA naught is nothing but what is happening? XA by minus RA. So if I take these two, then what will happen? I can write tau as CA naught XA CA naught divided by minus RA. That is what I wrote here. If I do these two, then what will happen? V by FA naught is nothing but XA by minus RA. Then we can write V as XA FA naught by minus RA, or you can compare these two because these are all equal. V by FA naught is tau by CA naught, or if you want to write tau as V CA naught divided by FA naught. Right, that is what I did in the previous one. Yeah, tau is nothing but CA naught V by FA naught. That is what you are getting here. From this only we get. This is the what do you call? Whatever equation you want to name. This is the big equation. From this only, whatever way you get, either you can compare 1 and 2, or 2 and 3, or 1 and 3 to get different expressions. So this you get from equating these two, and earlier equation what we got here, this we get from equating 1 and 3. 1 and 3. So in terms of conversions, we can put tau CA naught is XA by minus RA. Minus RA is K into CA. So tau K is XA by 1 minus XA. So in the both the cases, you are getting tau K. Not only here, even if there is a second order also, you get a tau into K. Tau is the space time, which is nothing but volume by volumetric flow rate into K. K is nothing but the rate constant. So tau K for a first order process is XA by 1 minus XA. This tau K for a first order process, what will happen to the unit for this tau K? What is the unit for tau? Yeah, K tau. Otherwise, some people call it as what is it? K tau. Some people in books they call K tau. So what is the unit for tau? Tau is space time. It is having a unit per second. Seconds into tau K. K, what is the unit for the first order process? K. 1 by second is the unit. This second cancel out. This tau k is dimensionless. Tau k is dimensionless for a first order process. But for a second order process, tau k is not dimensionless because k will have a unit of moles per liter. Extra term will come because concentration term will come. So k tau for a first order process is a dimensionless quantity. This k tau is called as, very important thing, Damkohler number. That is called as Damkohler number. The very important non-dimensional dimensionless number, just like your Reynolds number or Smith number or Nusselt number or Prandtl number or whatever number you are getting in heat transfer, mass transfer, and fluid mechanics, right? So in reaction engineering, we too get some numbers. One is Damkohler number. The other one, especially, we get in terms of what do you call non-idealities. We get one more number. Thus, what is that number we call? I'm not getting now. Let us, when we go there, we'll just see. Damkohler number, what is this? It is a dimensionless number. That is a Peclet number, right? That now I got it. That in that fourth unit you get, right? So it is a dimensionless number that helps us to make a quick estimate of the conversion that can be achieved in a reactor. Now we are taking a first order MFR with the expansion factor 0. When the expansion factor will be 0? When there is a liquid phase reactions. Liquid phase reactions, your expansion factor will be 0, whereas gas phase reactions, you cannot take this as 0. So for an expansion factor 0, tau k is XA by 1 minus XA. From this we can write XA as tau k by 1 plus tau k. For a first order reactions, tau k is called as a Damkohler number. We can write XA as Damkohler number by 1 plus Damkohler number. It's a very important 2 marks question. Or if you are going to a gate to write MTech thing, they'll give you some value of Damkohler number and they will ask you to calculate the conversion. Very important. Again, this equation is valid only for a first order process. It's not that any order you can take. Only for a first order process, your Damkohler number is tau k because this is dimensionless. Other than the first order process, your Damkohler number will have some dimensions, right? Or tau k will have some dimensions. Then you cannot tell that it is a Damkohler number because Damkohler number is dimensionless. Only for a first order process you will get XA is Damkohler number by 1 by Damkohler number. Now what is happening? If the Damkohler number is very high, that is tau k is very high, K is going to be a constant, especially for a temperature. When you are having Damkohler number high, that means that tau is more. Tau. What is tau? Tau is the time spent by the molecule inside the reactor. The more the time spends the molecule inside the reactor, more will be the conversion. Right? Correct? Because the more the class you come and attend CRE, more chance is there for you to get good marks. Less classes you are attending, less marks you get, obvious. Even in the reaction engineering, more the time the reactant is spending inside the reactor, more will be the chance of the conversion. So that is true because here you can see Damkohler number very high. That means your tau is very high. Tau is very high. Definitely your XA will be very high. That is what a very high value of Damkohler number indicates a very high conversion. Why? Because Damkohler number is tau k or k tau. K is going to be constant because we are assuming it is first order and you are not changing the what you call temperature. Therefore, tau is going to change. So tau high means more residence time is there, more the time is spending, the molecule is spending inside. Therefore, high conversion. Low value of Damkohler number indicates low conversion. So this is one thing that if the Damkohler number is less than 0.1, your conversion will be less than 10%. And if the Damkohler number is greater than 10, obviously you will get K tau or XA as greater than 90. That is, the conversion is greater than 90. It's a very important 2 marks question. What is Damkohler number? Especially in here. Okay. What will happen if this is not 0? If this is not 0, then especially for a gas phase reactions, then we have some task into some other extra work, right? That's what we'll see now. Because when it is not going to be 0, again the same first order kinetics, we know that V is V naught into 1 plus sigma A XA. From that we can write CA as CA naught into 1 minus XA by this particular thing. So tau CA naught, this you are getting from the MFR equation. Tau is CA naught XA by KCA because minus RA is first order, K into CA. We are writing CA as this particular thing for a variable volume. CA is CA naught into 1 minus XA by 1 plus epsilon A XA. You substitute that CA here, then rearrange, then you are landing with this particular equation. K tau is XA into 1 plus epsilon A XA divided by 1 minus XA. If the expansion factor is going to be 0, then you are landing with K tau is XA by 1 minus XA. But if the expansion factor is not 0, this is the expression which you need to remember. So always, whenever there is a gas phase reaction or changing in volume, you get extra term, this 1 plus epsilon A XA. So you need to integrate or you need to derivate that term also, right? Yeah, I think again plug flow reactor. I don't think I can complete this in 5 minutes. But if you are giving extra period, I can complete. I thought of completing this also, but I don't want to complete. Any doubt? Yeah, that's all for today. I think this new topic, I don't think I can complete because too much explanation is required here. You know, it's not that easy to understand this fellow. This fellow is not easy fellow to understand. Though this fellow is going in a tube, this fellow will make our life very difficult. It's not like this fellow where he is going out. This fellow is like a politician. Before coming to a party, he will have some ideologies. After coming to the another party, his entire ideology will be changed to according to the party which he joined. That is why this most famous example is the political fellow. Don't make that I'm supporting someone, just to make my point clear I gave, right? So that is what we tell, here how much is there, the same thing here, right? So whatever party policy, everyone will follow the same. But this fellow is not like that. This fellow is like a cube, right? It goes, one fellow goes in, that fellow should come out first. The second fellow goes in, he should come out second, not first. So that condition we make, then the life becomes much, you get extra term into picture that we'll see in the next class then. Yeah, today's class, any doubt? Yeah, you can talk to me. Today we discussed about the most important performance equation for the CSTR, the performance equation for a CSTR or MFR or whatever back mix reactor. Different names is there. Both, everything is same. Either it is back mix reactor or continuous stirred tank reactor or a mixed flow reactor. It is V by Fa naught is tau by Ca naught is Xa by minus Ra. This somehow you remember. This is our now Bible, Bhagavad Gita, or Quran, or whatever it is for CRE, right? This equation, it will come till CRE1 and CRE2, right? So this is the most famous, very big equation. Okay. Then we discussed about a Damkohler number, which tells that as the Damkohler number increases, your conversion increases. Why? Because Damkohler number is tau k or k tau. K is going to be a constant for a first order process, whereas tau is the volumetric flow rate divided volume by volumetric flow rate, otherwise called as the space time. The more the tau is there, definitely the conversion will be very more. Yeah, I stop here. I think if any doubts, I can take it and then close this. Yeah, any doubt? I stop the recording now.